All right, hi. So I'm Andrew Kim. I'm a software engineer based in Toronto, Canada, where I work remotely for DigitalOcean. So my talk is going to be about our globally distributed container networks and how we integrated Kubernetes directly into our data center networking to offer what we think is a very effective networking model for our engineers. So my talk is going to be a technical deep dive, and my hope is that this talk gives you enough context that you can actually build a similar container networking for your own clusters. And if I didn't give enough context, I'd love to chat with you about how to do that for your clusters. So before going there, though, I do want to provide some background on Kubernetes at DigitalOcean. So our first production deployment of Kubernetes was way back when Kubernetes version 1.1 was released. So that was roughly 2 years ago, early 2016. And at that time, we were experimenting with Kubernetes because we wanted to reduce the operational overhead that a lot of engineers were struggling with. So we wanted to create a consistent platform that made it really easy for developers to deploy applications into production, which I'm sure everyone here kind of had that similar story. So as we were looking into adopting Kubernetes, we faced a few challenges. One of them being that Kubernetes was a moving target, and it still is today. So best practices and features are constantly changing, or sometimes just being deprecated. And we also found that because Kubernetes offered so many features and knobs that you can tune, a lot of developers just didn't know where to start. So on top of that, the general impression of the time was that Kubernetes had too much YAML, and no one really wanted to learn what the metadata, the API groups, and all that stuff was. So out of that, we built an internal platform called DOCC, which stands for DigitalOcean Control Center. So DOCC is a multi-tenant internal PaaS built on top of Kubernetes. It's a very simple API layer that translates a specification that we maintain into Kubernetes resources. What's really powerful about this is that it's built with simplicity in mind, while also promoting and sometimes even enforcing some of the best practices that we think that you should follow when you deploy applications with containers and with Kubernetes. So some examples are if an engineer deploys something with the latest tag, we'll just block it and be like, no latest tag. And if you deploy an application into production and it does have an metrics endpoint, we'll just drop that too. It also meant that there were no huge files of YAML for developers to onboard them on our platform. Today, it's a little bit different where we have some engineers who really want that kubectl access and is okay with managing YAML, and there are some engineers that don't, but that's kind of a different story for another talk. And as much as I do want to talk about the internals of DOCC more and kind of the motivation behind why we did this, I don't have time, but we did have previous talks at previous KubeCons that you can look at. So 2 years later, and we're managing DOCC at a pretty large scale. And DOCC manages a lot of applications across all our data centers and across all our environments. What we found was really good at this large scale was that Kubernetes provided an excellent multi-tenant environment where resources were utilized more efficiently, where we didn't have like a single machine running this really small microservice. And it did an excellent job of making sure containers were running where they should be. And we find that Kubernetes provided all the great tools that it made building a platform really easy. So it was a great platform to build a platform. On the flip side of things, once we're running at a larger scale, we faced into a few challenges, and it was mostly around our networking. So we found that our initial design of our pod networking was fast enough for a majority of applications that are on DOCC, but it wasn't fast enough for the applications that were kind of latency sensitive and had really high throughputs. We also found that our container network wasn't intuitive. So we had source and destination NATing, and developers never really knew like which IPs were private and which IPs were like the external ingress-facing or public-facing IPs. And so we had to explain to developers a lot what those different components were. So I do want to dig a little deeper into why this was the case. So since we were pretty early adopters of Kubernetes, when we built our first production cluster, we used what was kind of well known at the time, which was an overlaid pod network with flannel. So this diagram kind of shows the path of a packet between two pods using this overlay. And I'm not going to go into too much detail into how this works, but the idea was that the packets went through a lot of different abstractions and different layers on the kernel for that pod-to-pod communication to work. So some challenges with this pod network topology was that the packet overhead became more and more impactful to performance with higher throughput. We also didn't like how every node in the cluster had to have a route for every other node in order for the cluster networking to work, because that made operating the individual nodes extremely difficult. We also didn't like how IP masquerading was essentially mandatory for any cluster network to work. So on top of this, because we had this overlay and it's confined to the cluster only, if we wanted to ingress traffic into the cluster, we had to set up, as I'm sure many of you know, ingress controllers. And if you've ever administered ingress controllers, you know the network ends up looking something like this, where the ingress controller pods are configured, usually with a host port binding, or they run on host network, so that they can actually receive external traffic for the cluster. So I just want to do a quick poll. Raise your hand if you've used ingress controllers in production. Okay, that's a lot of you. Okay, raise your hand if you have a love-hate relationship with ingress controllers. Okay, it's like half of you. And I'll tell you why. Okay, well, I definitely have a love-hate relationship, and I'll tell you why. So what we really liked about ingress controllers was that we were able to standardize how traffic came into the cluster. So we can set connection timeouts that are global to the cluster and all those things. And we were able to use a lot of the Kubernetes primitives to build mechanisms to kind of automatically fail over in case we lost a node that's running an ingress controller. So how do we do this? So we did this by running our ingress controllers as daemon sets with the node selector. And then there would be this another service called label controller. And what it did was it always ensured that there were enough healthy nodes with this label. And then it would see kind of the state of the nodes with this label. And then it would sync this wildcard DNS entry that we use for the cluster. So that would ensure that there was always enough nodes running the ingress controller. And if we move labels on the nodes for whatever reason, the DNS synced automatically by label controller. And then we can actually do this kind of stuff a lot, that we even coined the term label development. So as you can tell by now, this was really complicated and difficult to operate. It worked, but nonetheless, very complicated, and no one really wanted to kind of explain how this works to anyone. So on top of that, we had IPs being NAT'd, both for incoming and outgoing traffic. So when an outside client makes a request and the ingress controller proxies the request to a pod, the pod would see the source IP as the ingress controller instead of the actual client IP. Likewise, if pods talk to services that are outside of a cluster, the source IP would be NAT'd to whatever the node IP was, which is kind of a requirement because if the source IP was the pod IP and the outside application doesn't know how to route to that pod, the networking wouldn't work. So it had to be the node IP for this setup to work. So with all this in mind, what was lacking was that there was too much overhead from packet encapsulation. It was extremely operationally complex to manage this hacky node labels and DNS syncing. It wasn't reliable enough at a large scale. So once we had hundreds of nodes in a cluster and we lost an ingress, it actually affected a lot of applications in that cluster. And there was lack of visibility for source and destination IPs. So what we wanted in this new network was something that was simple to operate, had better visibility for source and destination IPs, something that scales with the cluster. So as you add capacity into the cluster, you're automatically scaling that ingress capability. And we wanted something that was just generally faster and didn't have so much overhead on the actual node. So we started doing some discovery around what this networking might look like. And it was important that what we designed initially and put into production was done right the first time. Because we know from experience that it's extremely difficult to actually change the container networking on a cluster that is actually already serving production traffic. And if you did build it incorrectly, you always had to build a new cluster and then set the networking correct there, and then you have to move all your pods over, and then you have to deprecate that cluster. And I've done it once, and it's a big hassle, no one wants to do it. So during this discovery, Mac Browning, my manager, had a really interesting idea and asked, what if we can directly connect to a pod or a service from anywhere on our network, which would essentially eliminate this barrier, this imaginary barrier we had between what we called this regular network and what we called this container network, which was always known to have this complex overlay and abstraction that developers had a hard time understanding. And it was hard to figure out what this might look like without grasping a better understanding of what our data center networking looked like. And understanding the internals of our data center network is also important to understand how we efficiently built this globally distributed network. So I'm going to be starting out with what we call a pod. And it's not a Kubernetes pod, but it's a pod kind of in the networking world, which in this context represents a single component of compute and network in our data centers. You can think of a pod as a building block for our data centers, where we host physical machines on racks that are connected over an aggregation of switches. So you can see in this diagram, at the top of each rack, you'll have a pair of switches, which are the leafs in this diagram, which are also often called the top-of-rack switches. So we run 2 top-of-rack switches per rack for redundancy, and then each server in the rack is connected to each top-of-rack with a 40G connection. And then linked to each top-of-rack is another tier of switches called the spines. And each spine switch would then actually be connected to all the top-of-racks in the same pod, providing kind of that extra layer of redundancy, but also allows a lot more bandwidth into that comes from the other parts of the data center. And to connect pods together, you have another aggregation layer called the core switches. And then if you want to kind of scale up the pods horizontally, you would then connect them through the core switches. But even then, you may want to scale out even further, which you can do by adding new pods connected to this new layer of core switches, which we call zones. And then the core switches of each zone would be connected so we can still have networking across all the different pods and zones. And so I'm sure some of you are asking, why do we need this? Because it seems really complicated. And the reason why so many data centers are designed this way is because there are limitations with how many physical connections you could have per switch. And even in theory, if you can create a magical switch that had thousands of physical ports that you can actually connect every single machine in the data center to, those switches would actually just end up being single points of failure for your data center network. So with data centers hosting thousands of machines, these sorts of networking topologies were created so we can actually connect our network in a way that provides enough bandwidth and enough redundancy for our use cases. So really what we wanted was some way to integrate closely with this data center network, because we know that data center switches are fast and reliable. So the switches used in data centers are programmed at the hardware level, making it significantly faster when making routing decisions. And there's also an extremely high level of redundancy that's kind of provided by the topology that I just showed. So how do we do this? How do we integrate our systems with this data center network? So it turns out there's actually a protocol that's older than probably most of us in this room called BGP. And it's a protocol that lets us actually communicate with the switches to actually configure routes in our data center. So in short, BGP stands for the Border Gateway Protocol. It's an inter-autonomous system routing protocol. And really, BGP is kind of the protocol that's kind of keeping the public internet together. And the way it works is that the internet really is this interconnection of autonomous systems that are built upon a system of trust. So these autonomous systems can be DigitalOcean, Google Cloud, or it's your internet service provider. And these autonomous systems are uniquely identified using autonomous system number, or an ASN. And they appear amongst each other to kind of share routing information, either about itself or about another system that it peers with. So I am skipping a lot of important details on how this really works, but this is kind of the gist you need to know for this talk. And just like how there are public and private IPs, there are also public and private autonomous systems. So within a single autonomous system, you could have many smaller autonomous systems that are peering with each other, sharing routing information that is only contained within that larger autonomous system. So going back to that network topology in our data centers, you can think of each tier in this topology to be an autonomous system. And each of them are peering with the switches that it's directly connected to. And each data center, you can imagine, is a public-facing autonomous system that's kind of advertising routes to the other public autonomous systems in the area. But there's also BGP peering that happens between our own data centers, which are usually connected by dedicated links that we manage to give us more predictable and reliable transport between our data centers. So this is what we call our backbone network. So with this in mind, we start to think about how we can fit Kubernetes clusters as these BGP autonomous systems. If we can do that, it meant that we can use BGP to dynamically advertise routes in our data centers and propagate IPs in our clusters into our entire backbone network. And luckily, due to the nature of this class topology, we don't necessarily need to peer directly to all the different tiers different tiers of switches in our data centers. We can just peer with the top of rack above each server, and the top of racks would then peer to all its known peers, and then so it would peer with the spines, and then it would peer to the core of the network. So that meant from a node per node configuration standpoint, and kind of all we had to do from there was to know what is the internal autonomous system number for the cluster, and how do we actually peer with this top of rack switch? So what is the IP of the switch, and what is the autonomous system number that the switch is, the top of rack switch is? So to accomplish this, we used a really cool open source project called kube-router. So it supports in-cluster, internal BGP and external BGP peering, which is what we use to peer with our top of rack switches. And you can also configure it to advertise the pod and the service IPs to all of its BGP peers. And lastly, it came with a lot of other features that we didn't anticipate of needing, but it ended up being pretty helpful for some of our current and future use cases, which I'm going to talk about more near the end of the slide, or the talk. So to go back to the top of rack configuration, really all we had to do on kube-router was tell it what is the cluster autonomous system number, which again, you can think of as this unique identifier for our clusters within this larger routing system that is our data center. And then how do you peer with this top of rack switch, which I mentioned earlier, which is what is the top of rack's IP and what is the autonomous system that it's part of. And from there, we can fully rely on kube-router to advertise the IPs we need to accomplish what we wanted, which was to advertise the pod and the service IPs in all our clusters. So by doing this, what we actually accomplished was that our service IPs were not only these virtual IPs that are only routable to applications inside the same cluster, but they are now these Anycast IPs that are available on our entire backbone network. And I say Anycast IPs because on the routing system, we now have this one-to-many association where we route packets to one receiver out of many, where each Kubernetes node that's running kube-router becomes a potential receiver for that IP. And we can easily achieve this by just running kube-router as a daemon set. And we found that this was extremely powerful for our engineers because it meant that just by creating a Kubernetes service, which usually was just done by DOCC, they're given this static IP that is globally routable and load balanced within our entire backbone network. And with it also came automatic health checking, graceful termination, and all the kind of great features that we know Kubernetes is great at. And lastly, that IP was completely owned by service owners. And my team only had to worry about how are the IPs actually being advertised within our data center, and how many IPs do I want to allocate per cluster, which is just setting some flags on the control plane. So we did work to provide these globally routable Anycast IPs to engineers. And though what we were aiming for was just a faster and intuitive and simpler to operate container network, we actually found a lot of interesting improvements and use cases that came out of having this topology. So the first one, which I've kind of talked about already, was that it became extremely easy for developers to start distributing their applications, because they can kind of deploy the same DOCC specification across all the regions. And then from there, it was kind of up to developers to either configure a per region DNS with that IP, or update our service discovery service with that IP. And engineers were really comfortable doing this because they knew that the service IPs that we give them are static. But to make it even easier, we realized that we can actually configure a shared subnet across all our clusters using external IPs. Meaning that if more than one cluster is advertising the same IP, we can rely on BGP's shortest path algorithm to find the closest data center running a service. And of course, this made it even easier for service owners because they're required to only manage this one single IP for a globally distributed application. And you can imagine that this makes a huge difference for some applications because they no longer have to cross our oceanic links to talk to services anymore. Also, since the pod IPs were also now routable within our entire data centers, we can actually disable masquerading for egress traffic, since we now assume that the application that's outside the cluster can respond back to that pod IP. So this made a huge difference when it came to monitoring our distributed systems, because we can correlate source IPs directly back to services, whereas before, we had to correlate source IPs back to node IPs, and then we'd have to check all the pods running on that node IP to figure out what service could possibly be talking to another service. So this was really helpful when it came to kind of monitoring things that pods talk to outside the cluster. This model also made configuring and operating the nodes in the cluster significantly easier. So we no longer had issues in production because this one node, for whatever reason, couldn't converge a route to another node. And these are the kind of the worst problems to have because like you'd have connectivity from one pod to another, but not other pods. But here, we can kind of just rely on the top-of-rack switch to route traffic for the pod network, which meant that on the nodes, we just needed the route that goes to the containers local to the node, and then we just need everything else, we can just send it to the top-of-rack, and we can rely on the top-of-rack to manage that pod networking for us. So this is an interesting one. So DNS was something that also kind of improved a lot with this topology. So one day, we remembered that kubedns has a service IP, which is the service IP that's injected into the resolver file for pods, which is kind of how the in-cluster DNS resolution works. Which meant that this IP that we use is also routable in our data centers, which meant that developers could easily use kubedns as a utility for applications that are not even in the Kubernetes cluster. But instead what we did was we actually set an NS record in all our regional DNS servers, and we would configure them so that if a query matches a cluster domain for any of our clusters, we could then have the regional DNS server query the regional kubedns service, and then kubedns would return either a service IP or a pod IP if you're using a headless service back to the regional DNS server. And then the regional DNS server would kind of give it back to whatever queried it. So this feature is actually really useful because from a service discovery standpoint, engineers didn't actually have to care if a service was deployed to a Kubernetes cluster or not, because the DNS domains can just work anywhere, as long as you have connectivity to that regional DNS server, which almost always you did. And we found that this made migrating applications into and out of our Kubernetes cluster significantly easier, because again, you wouldn't have to worry about what domains to use. If you're in cluster or out of cluster, you just use the same domain everywhere. And lastly, we no longer needed ingress controllers and kind of all the operational overhead that came with it. So we still kept them around because many applications depended on it from our previous generation of clusters, but we were able to make significant architectural changes that made it so much easier to operate ingress controllers. So instead of binding pods to the host network using daemon sets, we can just create a service for the ingress controller and then use the corresponding Anycast IP for the DNS. And this meant that we didn't have to do this magic with daemon sets and node labels. We can just run the ingress controller as a deployment and just use the service IP. So like any big change in our networking or kind of any architectural change, we definitely faced some challenges, and there was definitely some trade-offs along the way. So for one, we were seeing this is what I call the proxy mesh. It's where you route traffic for a service to a node that isn't actually running any of the pods for the service. So then it reroutes traffic back out to another node, which causes unnecessary bandwidth between your cluster. So luckily, kube-router does offer a solution to this problem, which I'm going to talk more about shortly. Next thing we noticed was that we now had this uniqueness requirement for the pod and service IPs we were using across our clusters. So in our previous overlay networking, this was never a problem because we can easily just use the same subnet for all our clusters, and since those IPs were contained in the same pod network, we didn't care if they overlapped. So when creating clusters, we now had to be more resourceful with how large the IP prefixes were. And this became very important in capacity planning because there's only so many private IPv4 IPs that you can actually use in your entire network globally. And lastly, BGP route convergence and rebalancing was difficult to monitor. It still is difficult to monitor. So as routes are added and removed in our clusters, it was difficult for us to gain visibility into how quickly those routes were converging over our backbone network. So in general, we found it fast enough to handle pretty much most of our failure scenarios, but having more visibility to the path of a packet outside of our clusters is something we definitely want to work on. So luckily, we do have very experienced network engineers that we can page during incidents who kind of do have better visibility there. So with these challenges in mind, there are definitely future improvements that we want to make as well. So going back to the proxy mesh, the reason we have this proxy mesh is because all the nodes in our clusters are advertising all the service IPs. And this is okay since we know that any node can receive traffic for a service IP since its proxy can route it to the right node eventually. But there are cases where you really want to reduce that proxy mesh, especially for applications that ingress a lot of bandwidth. And by following this model, you're actually doubling the amount of bandwidth you actually need. So kube-router does provide a simple solution to this problem by specifying the service's external traffic policy to local. When you do this, you configure the proxy to only route to pods local to the node, and then kube-router would only advertise routes if the pod for that service actually exists on the node. So doing this would actually eliminate the proxy mesh since the top of racks only route to nodes advertising that IP. And it's worth noting that by doing this, we would also preserve the source IP for ingress traffic, whereas with our current model, we still have natting for the ingress, because we have the source natting that happens from kubeproxy. So something else we were experimenting with to reduce the effects of that proxy mesh was something called DSR, which stands for direct server return. So this is a feature also supported in kube-router. So in short, the way it works is you end up modifying the packet's return address as it goes through the proxy, so that the receiving pod can actually, ends up returning packets directly back to the client instead of going back out through the proxy. So this is a really neat feature, and you'll find it used in a lot of large-scale load balancers. But we found kind of less of a need for this since we can just rely on that external traffic policy I was talking about earlier. We also want to see what it looks like to expose Kubernetes services directly to the public internet by advertising the public IPs straight from kube-router. So there are definitely a lot of considerations here, such as what does BGP route convergence look like when you're peering with all these publicly available autonomous systems? And of course, DigitalOcean, since we are a public cloud, we already do that at a pretty large scale. But if we wanted to know how it could actually, but we want to know how it could actually change the way developers actually manage their applications when they have kind of that control. Also, for a Kubernetes cluster that's receiving public traffic, what sort of pod security best practices should be in place so that this is actually doable? And what does it look like to use kube-router's networking policy feature to enforce stronger ingress and egress rules for our services? And lastly, we want to use IPv6 with our containers. We're not there yet, but we'll get there one day. Okay, so to recap, we found that there are a lot of interesting ways to design networks, especially when you have that context, like when you're in the context of a data center. So we found that the combination of using a protocol like BGP that is widely used in data centers and new technologies like Kubernetes can be extremely powerful. The combination of relying on Kubernetes to manage services and endpoints, and then being able to sync that state into the context of our data center networking gives us a lot of interesting ways to tackle common problems in distributed systems. More importantly, though, we found that designing a container network that is simple and intuitive to understand goes a really long way. There was definitely a journey for my team trying to understand the data center networking and adopting new technologies to make this work. But what we actually ended up offering to our engineers, which was this extremely simple to understand networking model, made a big difference when it came to adopting containers and making it easy for engineers to actually build reliable applications. So there are quite a few topics I didn't get to cover. We definitely learned a lot kind of running this in production. One of the things I really wanted to talk about was, can you actually do this on the cloud? Because in my context, we actually have access to the data center networking, and you can do this on the cloud. And there is definitely some more architectural and security considerations that I didn't get to cover. But I don't think I have time. But if any of these topics do interest you, please approach me. I'd love to chat. All these things kind of really interest me. So if you have any opinions or you want to chat more about this, please approach me at any point during the conference. And with that, thank you for listening to my talk. So before I do Q&A, I did want to take a second to announce that With the many years of experience we have running Kubernetes in production, we will be providing a managed Kubernetes offering soon. So, questions? No, so well, the networking model here was for the Kubernetes clusters we use to actually manage the internal services we have. But the droplet networking would be different. Yeah, but obviously we definitely use BGP in like the public internet. But yeah, so I'm actually not on the team that manages the droplet networking, so I can't tell you. Sorry. Yeah. Sorry, I can't hear you. Okay. Yeah. Yes. So the question was, have we considered using route reflectors? Essentially, route reflectors let you, like if you have a node with, if you have a cluster with 100 nodes, maybe only 5 of them are actually peering with the top of racks, and then the other 95 would peer with the nodes. That's kind of what route reflectors do. We actually did not have to use route reflectors yet, and that's mostly because kind of the switches we use are actually really beefy and powerful, so we didn't have to do that yet. But it's definitely on our, if we have scalability issues, this is the first thing we want to try is use route reflectors. Yeah, I'll get to you next. Yeah. Sorry, can you repeat that? With external IPs. Oh, so that's part of kube-router's features. Is it also checks the external IPs that are attached to services. Oh, right. So we don't actually do public IPs yet for the cluster, but we would probably get a pull from our networking team if we want to do that in the future. Yeah. Yes. Yeah, so we don't do network policy enforcements yet, but kube-router does support it, and the way it works, oh, sorry, I'll repeat the question. So how are we enforcing networking policies between our pods and between our clusters? So kube-router, so there's an actual API in Kubernetes that actually has a spec for what a networking policy looks like, and kube-router is just a consumer of that network policy type, and then it will create kind of IP table rules on the actual nodes to enforce that policy. So there's like an ingress and egress spec that you can specify. So that would be up to the developers, because the developer knows like what subnets the. So if service A in cluster A talks to service B in cluster B, the developer should know what the source and destination IPs between the clusters should be, so they can set the network policies themselves. Yeah, we haven't hashed that out though, because we haven't used network policies yet, because this is all in kind of our internal network, so we don't have to worry too much about network policies, but we definitely want to dig into that. Sorry, can you repeat the question? I couldn't hear you. Okay, so the question was, do we plan to use Yes, so the question was, do we plan to use Calicoes BGP feature? When we were initially kind of looking at technologies to use for this, we were debating between Calico, kube-router, or to just build our own. The reason why we didn't stick with Calico is because it didn't actually support advertising the service IPs, and we'd have to build that in. And so kube-router already did the pod, and the service and external IPs, and it also supported network policy, so we kind of just went with that.
Just a quick thing on the standard thing for advertising external BGP, metal LB. At the moment, there is a conflict
Yeah, so the question was around why we didn't use metal LB, is that? Yeah, essentially we didn't use metal LB because we really want that the pod IPs to be advertised, and metal LB does not support the advertising of pod IPs. And the reason why we actually wanted to use pod IPs is this really interesting use case where we actually want to run Prometheus outside of the actual cluster because we don't want this dependency loop between our clusters and Prometheus. And with all the pod IPs kind of being where you can actually scrape the pod IPs outside the cluster, you can actually have managed Kubernetes, managed Prometheus outside of your cluster, which is why we wanted the routable pod IPs. Yeah, so the question was, do we allow automatic, like dynamically assigned service IPs? And for most services, we actually let the control plane, the Kubernetes control plane, assign the dynamic IP out of the subnet we tell it can use. And then from there, as long as you don't delete your service, then that's pretty much a static IP for you. And even if you deleted it, if you knew what the IP was, you can recreate the service and specify exactly which cluster IP that you wanted, assuming someone else didn't create a service in the meantime that used that IP. Yeah.
I apologize if you covered this, but do you do anything with Anycast or like multiple advertisements to allow services to reach the closest thing?
Yes, I did cover that, so I'll chat with you after, yeah. Yeah, no worries. Okay, I don't know how much time we have. Yeah, so I think we're out of time. So yeah, I'll answer more questions. Come to the DigitalOcean booth. I'll be there most of today and tomorrow. All right, thanks.